Welcome back, everyone. This is another lecture of MIET 392 Underground Mining here at Bluefield State University. And so far in this course, we've been talking a lot about just, overviews of different mining systems and that sort of thing. And I think we've covered that pretty well up to this point. And so what I want to do now is move into something that, well, this is, one aspect of longwall mining that really sets it apart from, rim and pillar and that sort of thing, and that is the shield design itself. So this lecture is titled Longwall Shield Design. You'll find out as we go along through the course that many aspects of underground mining, ventilation, the concepts with roof control and stress redistribution and that sort of thing, they carry over from one type of mining to the other. The principles remain the same. But in this case, the design of longwall shields is one thing that separates longwall mining from other forms, and this is something that you need to know. So let's get right into it and talk about how we design longwall shields. So the main components of a shield are shown on this slide, and you have the canopy and the hydraulic legs, and of course the caving shield in the back, and then the lemniscate links, as you see there, connecting the base to the caving shield. You also have the hydraulic legs, which you can calculate, setting and yield pressures for, and also the rigid base and the double acting ram in the front, the push ram system. So you have all of those pieces, and what we're going to do is determine the load that's applied to the top of the shield and where that load is at on the canopy. Okay. So elements of longwall shield design. First is the roof load or support capacity. You want to design the capacity of the shield, and to do that, the basic question you're going to ask yourself is, does the roof hang up? And you'll see what I mean here in a minute. Two is the structural integrity and the stability of the powered supports. Are your shields big enough? And are they designed in such a way that they can't topple over, right? Also, there's the interactions among the support, the roof, and the floor. Impacts the dimension of shield elements, and also, it impacts the friction that's applied to the between the roof and the top canopy and the floor and the base, which does impact the resultant moments that act upon the shield. And then finally, you need to consider the service life, considering that shields are cyclically loaded, right? They have loading and unloading, repeated cycles of this over and over again, and they experience fatigue over time. So here's the procedure from Sid Ping's Longwall Mining 3rd edition, which is where all of this came from. The procedures for designing a shield support. So 1, preliminary determination of component sizes. So we're going to be considering the mining height, the prop-free front, so how far, how much space you have in front of the legs, right, between the legs and the face conveyor. You also consider ventilation requirements, and then other considerations. Then second, determination of the roof and lateral loadings by considering the characteristics of the immediate roof, the thickness, and the caving conditions. So we're going to determine the caving height, basically, of what we expect in the gob. And then we also will determine the gob loading on the caving shield and characteristics of the main roof movement. So that's step 2. Step 3 is determining the load-bearing capacity of floor rocks and water conditions. 4 is the geometrical configuration. So based on the analysis of stability, right? So the external loadings and the supporting efficiency. We'll be using those. You can use those to determine what this shield configuration actually needs to be, the components of the shield. And if necessary, you can revise that and repeat the analysis until you're desired conditions are met. 5 is structural design, determining the actual size and stiffness of each element by performing static stress analysis, which a lot of stress analysis have been done by various manufacturers. There's also been some of the analysis completed at the MIET roof simulator, but there are ways out there to find if you need this information, if you need it. And then, of course, testing of the full-size prototypes, which is still done. It is no longer done at the MIET roof simulator in Pittsburgh, as the shields are too large to fit in that frame anymore. But yeah, so there has been testing of shields in the past in multiple ways. So, the preliminary determination of overall mining dimensions. So we have to pick a shield, right, that fits in our seam, okay? And it does vary from place to place in a mine. But there is the hydraulic legs have a stroke to them, right? So you can have a single, hydraulic support or a double. And in this case, you can calculate the maximum and minimum working heights of the support by using the following equations. Where H is the average seam thickness, okay? So you got the seam thickness. Delta H is 1/2 of the maximum change in seam thickness. So the range of seam thicknesses you have. And then C is the roof convergence at the face area, and C sub R is the height of rock debris in the floor which the base sits upon. Those are, numbers. It tells you that usually that's 1 to 3 inches per mining cycle, but could be up to 6. Okay. So we add all those together, though, we can get those two values. And for a single telescopic leg, we find that the ratio between the two is 1.72. Okay, that's because there's space within the leg where it can't collapse all the way. It has fluid in it, that sort of thing. And the ratio increases with inclination from the vertical, right? So the more horizontal your legs are, your shield, it increases, but then resistance decreases, right? The amount you're actually pushing up on the roof goes down. And so there's typically a compromise there where the legs are at 20 to 30 degrees from vertical. So for a double telescopic leg, H max over H min is 2.5. The prop-free front concept refers to the distance from the face to the shield leg. So how much space there is, even beyond the pan line, right? So all the way to the face. And it roughly equals the shear width, AFC shear width, the web width, plus travel way width before shears cutting, or plus web width after the cutting. So you can either have it before or after. And it ranges typically from 12 to 16 feet. Okay. The size of the prop-free front depends on the width required to install the cutting machine, and the face conveyor, and the location of space for crew travel. Large prop-free front is not desirable for a weak immediate roof, which requires proper immediate support near the canopy tip, right? So if your roof is weak, you need to get those shields reset as fast as you can and get the canopy tip as close to the face as you can, because you want supported loads, in this area very small, so you want to keep them really, really tight. For a two-legged shield, the crew usually travels in front of the legs, with optimum width for travel ways of 2 to 3 feet. There you go. Ventilation requirements. So there are laws on that, and they do vary from district to district. But of course, if it contains high volume of methane, you're going to need a large volume of air. Okay. The minimum or maximum methane content allowed at the face is 1%, and the minimum air velocity, like I said, varies with district, but is commonly 400 feet a minute, measured at the 10th shield from the head gate T-junction. So 10th shield from the head gate, you measure, and most districts require 400 feet a minute. You may need more, you may need less depending on the district, but you may also need more than that depending on what gases are being released in your cold seam. But we won't be covering all that in this class. Basically, we'll just be covering the basics, because there's 2 other ventilation courses in this program, and there's plenty of time to cover all of those things. Other considerations, you need to consider transporting the shields, right? Both first-time installations and subsequent face moves. I can give you an example, Lila Canyon being one of those. When the new shields were brought in, they were too big, and they did have to mine some additional roadway so that they could transport those shields. That does happen, but you'd have to consider it, and it may be worth it to do something like that. And also for subsequent face moves. So its cross-sectional area in the collapse position has got to be able to fit in the entries. Right. Here's the dimensions of that influence a shield or influence shield design in a major cross-section. This is from Caterpillar, and you can see some of these dimensions listed here that we've talked about. We have that tip to face distance, the web depth, which is typically 3 feet or 3.5 feet, the travel way, the whole width of the shield, or in this, I would call that the length of the shield. Typically we consider shield widths 1.75 meters or 2 meters. So maybe that's width, but tip to the end of the caving shield is the length or width in this drawing. So how do we calculate the loads on the shields? How do we determine these external loadings? And I'm going to teach you the exact same method that was taught to me in one of Dr. Sid Ping's, the author of this book, one of his last courses on the subject. I was in class, and this is how we learned to do it. And so things have changed a little bit since then, but in reality, this is still the method that's most widely used for getting an understanding of what loadings could be on your shields. Here you do see some of the variables written here. Capital H is the mining height. H sub IM is the caving height. Remember I told you we'd be talking about that. F is the panel coal block. Also notice the width of the web cut. LSU is that unsupported distance between the shield tip and the face. And we have the canopy length, which is L sub C, the rear overhang, how far the roof overhangs that canopy. And then L sub E is the distance from the face line to the leg before cutting. Okay. And then we have theta is the caving angle, right? So you have blocks A and B that apply weight to the longwall shield itself in a static loading. And then as the longwall advances, eventually we will see that you have a periodic weighting, W sub 2, which is then later on added to the shield, okay, after the periodic weighting begins. So for the analysis of canopy loading, it consists of 2 components, the location and the magnitude of the resultant force. Okay, so we need to know the weight of W1, which is the weight of block A and block E together, and we can find that using the caving height multiplied by, that's not in this list, maybe it's somewhere else, multiplied by the density, multiplied by the center to center distance of the shield supports, and then of course we have alpha, the angle of seam inclination, and then we have a second component which divides that by 2 and then multiplies back through just to give you this weight of the block, okay, which is finally, let's start over. So the analysis of canopy loading consists of 2 components, the location and magnitude of the resultant force. So the weight of the immediate roof, W sub 1, on the support is the weight of blocks A and B together that we showed you, okay? And that's equal to the caving height is a function, so it's a function of the caving height, the center to center distance of the shield supports, how wide the shields are, the angle of seam inclination, and the caving angle, right? So it's all a function of that. And of course, all those links, right, that add up either before or after the shear is cut. I would probably suggest using after, so you're supporting all that with the shield. You add all those. So it's all a function of that. weight on the block. That's sort of the easy part. And then the location where W1 acts on the canopy is then found as little w1 or lowercase w1. And it's also a function of the length, right? The caving height, the angle of the cave, right? It's all a function of that. And the canopy will, if W1 is greater than L1, okay, the rear portion of the canopy will be subjected to larger loadings. And that's typical if the roof overhangs. If it's weak and breaks ahead of the gob edge of the canopy, which is also possible, W1 is less than L1. That means a larger loading is on the front portion of the shields. Okay, so where it acts on the canopy is important, and this is how you calculate how far away from the face that is. So after periodic weighting, as I mentioned before, this results in WSU being added, and the location where it acts is important because you have the following two equations. Lowercase v sub 1, that was v sub 1, so that's the distance from the face where the resultant force acts, multiplied by the resultant force, is equal to W1 and W2, and little w1 and w2, which is the distance where W1 and W2 act respectively from the face. Okay? And then you have, so V1 is equal to W1 plus W2. That's that total resultant force, right? So we have the two weights together. And so what I've been teaching so far is the detached roof block method. Okay, and that example of a detached roof block is there again on the left side of the screen. The pros of this is that it's the simplest method. It's commonly used by operators and support manufacturers, but it could be too simplistic for some roof lithologies. And so there's two factors to estimate the height of this detached block. We can use the stratigraphic sequence and then use a balking factor to determine what that caving height's going to be, right? So here's sort of an example of the behavior of the detached block and how it operates in the lower Katanning seam in north central West Virginia. And so what you have in this case is the immediate roof is a gray shale, which does appear to, at least in this drawing, to overhang slightly. And then you have a relatively thick sandstone over top of that, which imparts a periodic weighting upon the long wall. So what I'm trying to show you here is that why this periodic weighting occurs. Okay, and that sandstone breaks, according to this drawing, every 8 to 13 feet, right? So every 8 to 13 feet, you'll repeat the cycle, and the loading will drop off, and it will begin to increase again. Although at the same time, you have a very thick gray shale above that also fractures. It's in the fracture zone, right? So you have a longer periodic weighting from it, and it's going to be even greater. You'll even see that even more so in the shields, and according to this, it breaks every 44 to 60 feet. So this is sort of an idea of what that block's going to look like in this scenario, right? So all we're doing is, once again, calculating the weight of this block on top of an individual shield. What's it holding up? And that's in this cave zone. So the height of caving has to satisfy the following condition, and that is H, the mining height, minus D, sagging of the lowest uncaved strata, will equal the caving height multiplied by K, the balking factor, minus 1. Okay? So balking factor can be thought of kind of like as a swell, right? And but it's in a form of a factor and not a percentage, right? So for example, 25% swell would be a balking factor of 1.25. So anywho, from that first equation, though, we have to assume that D, the sagging of that lowest uncaved strata, is less than the maximum sagging, right? So it's not going to break, and instead, that's where the caving stops at. And so from that equation, 3.21, you can rearrange that, and you just have H minus D divided by K minus 1. So the mining height minus the sagging of the lowest uncaved strata divided by that balking factor minus 1. And so here we have typical balking factors. We have original balking factors and residuals. So what this is, the original balking factors is when the roof first caves, right? So what your shields are usually holding up. When that roof first caves, you have a larger balking factor than you do if that gob is set down and compacted, okay? And what you see on the left is those balking factors range from just above 1 to like 1.8 for like a big sandstone, right? Big balking factor. Yeah. And then you see the residuals are much lower. They are 1.01, so basically 1, up to 1.35. Okay, those are much lower. So, if the height of the bulk material equals or exceeds that caving height, okay, then the weight of the detached block, it's pretty simple. It's that H multiplied by B, right? So we have the height of the block, we have the shield spacing, so that gives us the width of the shield, okay, with the density of the material, the length, the shield length, canopy length, right, all those L sub whatevers all put together, and we divide that by the original balking factor, minus 1. And so if we assume that there's a range that you could use for this, 1.1 to 1.5, that is where we get that the caving height is 2 to 10 times the mining height, right? That's where that comes from, and is here, right, in equation 6.4.6. But we found out over time in the 70s and the early 80s that using this original balking factor can in fact underestimate the capacity of required shields. There were shields that were lost, probably entire systems, Longwalls that were lost early on because of this. And what this did was it sort of created a trend towards inflating shield load capacities, right? And so they've inflated those over time, and they are a bit over what you'll calculate using this method with a modest balking factor like 1.25, right? There's good reason for that, though, in that if the loss of a system is so costly that you'll see that over design is more important than the amount of money you could have saved and gotten something a little more less likely to be stable, right? We're basically, when we actually do design something, we're designing it for a small fraction of the conditions that they'll actually be in. We use conservative estimates and safety factors, so we're designing for the 10% and not the 90%, right? That's basically what I'm trying to get at as to why the trends are the way they are and why it makes sense. So this does talk about all of that. Dr. Ping was a fan of the written word. And so the 70s into the 90s, you see increase in load capacities, right? And to calculate those capacities based on this number, yeah, you've got to use 1.1 or less for the balking factor, right? So that has to be used. But it does, like I said, produce these overrated static capacities that may not be necessary if you had started using a reasonable balking factor of 1.25. We might have just stayed there. I don't know. But we are going to talk about that here in a minute. There is another way to calculate the detached block, and Chin and Ping determined that if the strata or stratum will overhang, then you can calculate the weight of each overhang separately with these following equations. And these equations are going to make a lot of sense when you see the drawing, and they don't necessarily make a lot of sense now. But you have the length of the block and how much it overhangs, and then you have the resultant force, which is the sum of all of those. Okay, but you'll see this better in the following photo. But I also have all of the variables here, and what they mean. This design factor, because it was like a 1.1 to 1.25, right? This is for recalculating modern shield capacities. Okay, um, that those aren't maybe the actual um, bulking factors, right? They're not the actual. So that's what this is. It's got all of the different variables here. Like I said, this is going to make a whole lot more sense when you see the drawing. And you also have some ideas of what the tensile strength you might be looking at for the different materials as well. Here we go. Here's what you want to see. So it's the same detached block, except there is a series of beams that overhang the long wall, right? And I've been to my mind that looked maybe similar to this. It definitely had a whole lot of overhang, but I remember being in Pinnacle 50 quite a long time ago, back when I was, I think I was a sophomore, actually. So I was probably 19 or 20 years old, and I went to the Pinnacle 50 mine, went back on the long wall, and the plow was running, and the overhang there, at least at that part of that mine, was pretty significant. I mean, you could pretty much drive a bus through there. It was wide open. Whereas typically, like in the Pittsburgh seam, it's caved all the way up to the back of the shields, right? But like I said, this model, so if it's overhanging, you basically just calculate each layer of rock, the weight of it, where it's acting on the shield, and then you add those up, and it becomes a weighted average. And so we've calculated the weight, we've calculated where it acts, we've looked at two different detached block models, right? These block models, and we're not going to go into a lot of detail about this next section, but I do want you to be aware of how these resultant forces act on the actual shield, right? So the next step in shield design, and like I said, manufacturers have a lot of data on this. They've been doing it for a long time, but you have this resultant, force that's acting on the shield. Okay, there's also friction involved in the roof, right? You have the force up from the legs, P, right? The pressure in the legs, and they're acting at an angle of alpha, right? You could also have some weighting on the caving shield as well, this W, which could be involved in this. There's also the friction at the floor, the resultant, where that is located on the base. And then there's also what's not shown in this drawing. At least I don't think so. Is the hydraulic ram? That's the push ram, right? But all these forces are acting on the shields, okay? And you can take the sum of all these and the moments around the 2 points on the shield and calculate the resultant magnitude and direction in which force is applied to it. But like I said, we're not going to go into all that. We're going to stop at the attached block model. Can you calculate what your shield capacity is likely to be? That sort of thing. But I'm going to leave you with 5 key takeaways from Dr. Peng's book, just to better understand the concepts of how all this is working. Okay. And the first one is start with detached roof block, but use real geology. So what we'll be doing in class, we'll be using some mine's geology to sort of determine, what the mining height and the caving height is going to be. Or in a problem, it can just be given to you. But in real life, you're going to be using real geology from actual core holes or in-mine observations or that sort of thing. In your design, we can't control all of the variables, right? But the ones we can, we need to aim for the resultant force to be located in front of or in line with the shield legs, okay? It's better to have a front bias than a rear bias. You can tune this with some of the settings, including set pressure, right? Because that's going to change your friction. The angles of the legs, those can be adjusted, right? I'm not, prior to, purchasing it, but if you want to if you need that, you can change that. And then of course, friction, like I said, consider that to be a bonus, to help with this. It's not the end of the world if it's not there, that sort of thing. But it can help, right? Friction can help. And then number 4 is to keep the stabilizing ram in compression, right? And you can shorten that length, that D, to sort of pull the line forward. But it's best to keep um, your rams in compression. And then, of course, make sure to check the floor bearing capacity, not just the leg capacity, right? So we also have equations that relate to the floor bearing capacity, and you can calculate what the floor is capable of supporting, and whether or not you need some sort of shield that has a larger footprint or that sort of thing. So those are the sort of 5 key takeaways beyond the detached roof block model and how to do that.
All right, so there you have it. Basics of shield design using the detached block method, basically calculating the amount of load over top of a shield, within that caving zone that's going to be applied to an individual shield. So with that, I'm going to say goodbye for the week. This is the Bluefield Coal Show this week. Please come out if you can. And we hope to see you there. Stop by our booth and say hello. So thank you.